Welcome to the Ultimate Physics channel. In this video, we are going to solve some problems on relativistic momentum. Let's do a quick recap of relativistic momentum. We have already posted a separate video on this topic, a lecture video on this topic in this channel. So if you have not seen this video, I suggest that you please go back and check out that video before trying to solve problems here. The classical expression for defining momentum we know is momentum P is equal to mass times velocity, so m times u, where u is the velocity here of that particular object. And this is valid because classically this particular quantity mu is conserved when there is no external force. But special relativity makes us realize that momentum measured in one frame of reference is different from that measured in another frame of reference, which is in relative motion. Therefore, we need a relativistic expression for momentum, which is given by m as a function of u. That is, mass as a function of u itself. Mass itself is changing with velocity according to special relativity. Therefore, mass as a function of u is equal to m over square root of 1 minus u squared over c squared, which is relativistic mass. Therefore, accordingly, the relativistic expression for momentum P is given by P is equal to mu over square root of 1 minus u squared over c squared, which can also be written as gamma times mu. Let's try to solve problems based on this expression. The first problem, the speed of an electron is doubled from 0.2c to 0.4c. By what ratio does its momentum increase? What happens to the momentum when its speed is again doubled from 0.4c to 0.8c? We know that we have to use the relativistic expression for momentum here. That is P is equal to gamma times mu. This is the relativistic expression. We have to get the gamma factor, that is 1 over square root of 1 minus u squared over c squared. Now here two velocities are involved initially. Initial velocity is 0.2c and it is double to 0.4c. So gamma, if you calculate using this formula by substituting this as u here, you will get, let's say, gamma 1. That we are getting as 1.021. And when it is 0.4c, if you substitute 0.4c for u here in this expression, you get gamma 2. And that is 1.091. So let me write that this is for u is equal to 0.2c and this is for u 0.4c. Now the momentum changes therefore accordingly. So momentum goes from P1 to P2. When gamma changes from gamma 1 to gamma 2, or the velocity u changes from 0.2c to 0.4c. So if you calculate momentum P1, that is gamma 1 times m u1, and that is 1.021, whatever be the mass, and we know that it is multiplied by 0.2c. Similarly, P2 is gamma 2 m u2, and that goes from 1.091 m 0.4c here, right? Therefore, the ratio of these two momenta values is, let's say, P2 over P1 I take. That would be 1.091 times this ratio 0.4 to 0.2 is 2. And denominator you have gamma 1, that is 1.021. The mass factor is common in both these things, so yes, cancelling, and then numerator 0.4, denominator 0.2. So if I 2, I get a 2 factor, a factor of 2 here. So if I work this out, I get 2.137. So when the speed is doubled, the momentum changes from P1 to P2, and that is, it changes by a factor of 2.137 for this change in speed. Right. Now the question is, what happens when it changes from 0.4c to 0.8c? It is not going to change by the same amount because we know that this is a non-linear expression. It is not linearly changing because of the gamma factor. So the momentum in relativistic theory, it does not change linearly. It is non-linearly changing. Therefore, we are not going to get the increase from 0.4 to 0.8c by the same extent as 0.2 to 0.4c. Because here velocity is doubled. Again, you are doubling the velocity, but the momentum is not going to change by the same factor. So let's work it out. In this case, it is 0.4 to 0.4c to 0.8c, the speed. U changes from this to this. Let's say momentum now changes from P3 to P4 accordingly. Now our P3 is gamma 3 m u3. Our P4 is gamma 4 m u4. Gamma 3, if you work out using this velocity for u, that is 1.091. Again, gamma 4 on the other hand is 1.667. So if we substitute these values and get a ratio of P4 to P3, that is 1.667 times again 2, because the factor is again doubling. So it is 0.4 to 0.8, that is going to be 2. And here it is 1.091 for gamma 3. And that would be 3.056. So we can clearly see that in the previous case, the factor was momentum change was by a factor of 2.137, whereas in the present case, it is by a factor of 3.056. So as the speed increases, as we approach the speed of light, definitely this is going to increase by a larger and larger number. Right, let's move on to the next one. Find the force necessary to give a proton an acceleration of 10 power 19 meters per second squared when the proton has velocity along the same direction as the force, if the speed u is 0.01c, 0.1c, 0.9c, 0.99c. So 4 different velocity values are given and force is asked. So let's write the relativistic expression for force, that is gamma power 3 MA. We have derived this expression in our lecture videos on this topic, so please do check that out if you have not watched it already. This expression is valid only when the force is parallel, F parallel to the acceleration direction A. Only that is given here because it's same direction. It is given as same direction, that means force is parallel to the acceleration A. Under that circumstance, this is the relativistic expression for force. So our Newton's expression, force is equal to mass times acceleration in relativity is this. This is the relativistic expression. So Newton's law gets modified accordingly here. Now we have different cases. The first case is the speed when it is 0.001 0.01c. Again, we can work out the gamma factor for this. That is 1 over square root of 1 minus u squared over c squared, wherever u is 0.01c. If I work that out, I get gamma as 1.0002. So if I substitute that in the expression for force, that is F is equal to gamma cube MA. Gamma cubed MA is 1.0002 power 3. This is a proton, right? Here it is mentioned as proton. Its acceleration is given as well. So proton mass is 1.66 into 10 power minus 27 kg times its acceleration 10 power 19. If I put these numbers, I'm getting my force as 1.661, let's say that is, into 10 power minus 8 newtons, which is roughly 16 nanonewtons. So that is the force necessary to give a proton an acceleration from rest to a velocity of about 1/100th of the speed of light, 0.01c. Right, next value is u is equal to 0.1c. In this case, again, I use the same expression here, F is equal to gamma cube MA. Here, u is equal to 0.1c. So if I calculate gamma here, using that, I get 1.005. So if I work out force again the same way, where m is proton mass 1.66 into 10 power minus 27 and a is given as 10 power 19, I get a force of 1.685 into 10 power minus 8 newtons again. So this is like roughly 17 nanonewtons. So to increase the speed from about 1/100th of the speed of light to about 1/10 here, 1/10 of the speed of light, the force increase is about only 1 nanonewtons, right? Earlier case we got 16 nanonewtons, now we are getting 17 nanonewtons, so that's not much. The third case is interesting. When u is about 0.9c, this is a significant increase in speed. It is about 90% speed of light, right? In this case, we can again do the same thing, calculate gamma. I've done that already. That is 2.294. 2.294. And then gamma cube, force is gamma cubed MA, which is equal to, gamma cubed is this value whole cube, so it is 12.075 times 1.66 into 10 power minus 27 into 10 power 19. If I do, I get a force of about 200 nanonewtons roughly. So we can clearly see that more force is required now compared to 17 newtons, in this case 200 nanonewtons. And finally, the fourth case, if I do the same thing and work out for u is equal to 0.99c, that is to increase again by a further 9%, that is about 99% compared to the 90% that we took here. The third case here, 99%. For this again force, if you calculate by using the same method, you will get about 5,930 nanonewtons. So significant increase in force. So more and more force is required to step up, to increase the velocity close to the speed of light, right? a significant increase in force from about 200 nanonewtons for 90% of the speed of light. To accelerate the proton to about 99% the speed of light, we need about 30 times more force, right? For a 10% increase in speed of light, in speed rather, of the proton, right? Let's move on to the next one. The third problem, a particle having a speed of about 0.92 c has a momentum of 10 power minus 16 kilograms meter per second. What is its mass? It's very simple here, right? Because we have this expression P is equal to gamma times mu. We need mass here. P is given. So mass is P over gamma u. P is 10 power minus 16. In this case 0.92 c, so I calculate gamma 1 over square root of 1 minus 0.92 c whole squared over c squared. So if I calculate gamma here, I get 2.552 as the gamma. So if I substitute that here, 2.552 times 0.92 c, which is 3 into 10 power 8 meters per second. My mass is in kilograms now. That would be about 1.42 into 10 power minus 25 kilograms. So that should be the mass of a particle whose speed should be 0.92 c and whose momentum should be 10 power minus 16 kg meters per second. Right, so let's move on to the next one. A particle initially has a speed of 0.5 c. At what speed does its momentum increase by 1%, 10%, and 100%? Right. So when u is equal to 1% of speed of light, right? Sorry, momentum rather, sorry. This is momentum increase, right? Momentum increase by 1%. So first let's do for the given particle, u is equal to 0.5 c and momentum is p is equal to gamma times mu, and for 0.5 c, gamma is equal to 1 over square root of 1 minus 0.5 c over c squared. That would be 0.5, sorry, it's not 0.5, it is gamma is equal to 1.155. Now P is equal to gamma times mu, and that is 1.155 times m times u is 0.5 c. So I retain that as MC units, so it is 0.577 MC. That is the momentum. For the given speed. Now P increases by 1% in the first case. P increases by 1%. So the momentum changes from P to, let's say, P1. That is 0.577 MC plus the increase is 1%. So I'm saying it is 0.00577, isn't it? We add this, then it is 1% increase. This alone is 1% increase. as given in the question. And this would be P1, that would be equal to 0.583 c. Now if you have to calculate the speed for this momentum, what would be the speed? Because the mass is the same, right? So let's move on to do that. So in this case, we can write the expression as u over square root of 1 minus u squared over c squared is equal to 0.583 mc. Here also mu. This is the expression for momentum, right? So it is equal to this. So now the common thing is mass here, so I cancel this. So then I will write u over square root of 1 minus u square over c square is 0.583 c. If I square on both sides, I can write as u squared 1 minus u squared over c squared is equal to 0.3396 c squared for this square of this. So I get an expression here. So I write u squared is equal to 0.3396 c squared minus 0.3396 u squared. So it is 1.335. Rearrange the terms to the left and right side. I get 1.3396 u squared as 0.3396 c squared. And therefore my u is equal to square root of these two numbers, that is 0.3396 over 1.3396 times c. So if that I work that out, that is going to be u is equal to 0.5035 c. That is the answer. Now in the same way, I suggest that I'm not going to complete that one. 10% increase and 100% increase in momentum can also be worked out in the same way here, using the same procedure. Right. Let's move on to the next one. That is the fifth problem here, which is the orbital velocity of the Sun. About the center of the Milky Way, that is our galaxy, is 250 kilometers per second. By what fraction do the relativistic and the Newtonian values differ for Sun's momentum? So if I use the classical expression, I'll get a particular value for momentum, and if I use the relativistic expression for momentum, I'll get another value. And by how much they differ, because if the speed is only 250 kilometers per second, how important is using relativistic expression? That we have to understand, right? That is the reason why this problem is given. So let's try to work that out. Let the Sun's mass be m naught. We don't need the exact number here, so let's just use the notation m naught. Let m naught be the solar mass. If I use a classical expression, classical momentum, that is, let us call that Pc, P suffix c, that is m u, in this case capital M naught times 250 velocity kilometers, so I put a 10 power 3 here, and momentum units are kg, meters per second. M times 250 times 10 power 3. This is classical. So if I do relativistic momentum, that is, let me call that as PR, that is gamma times mu. What is the gamma for this? That is the question. If I work that gamma out here, 1 over square root of 1 minus 250 into 10 power 3 over 3 into 10 power 8. Both are in meters per second. So if I do that, I get a gamma which is 1.000, another three zeros, and then I get 347. 347. So the gamma is up to 6 decimals. No, there are only zeros, and then only we have some numbers that is 347. So the effect of relativity is going to be the seventh decimal place here, right? Because 6 decimals are again same as classical. So the relativistic momentum, if we calculate using this expression for this particular gamma value, I would write it is 1.123456347, 6 zeros and then 347, times the same thing, 10 power 3 uh, uh, into 250 kg meters per second, same units, right? So the difference we can clearly see between the classical PC and the relativistic PR is very small, and that difference is, if I do that, that would be this 3.47 times 10 power minus 7. Okay, 3.47 because this is seventh decimal. So I say that the difference in this case is a fraction they're asking, right? By what fraction these values are changing. So I say the fraction by which the momentum change. So fractional change in momentum is PR is higher, PR minus PC over PR. If I do that, I'm going to get 3.469, because there is a small difference, right? Into 10 power minus 7. Because the difference alone is 3.47 into 10 power minus 7, but you are dividing it by PR, and the PR is again 1.000000347. So that value, if you divide in the denominator, you get this value for the change, fractional change. So this is the fraction by which the classical and the relativistic momentum values differ. Okay, let's move on to the next one. An electron in hydrogen atom has a speed of 2.2 into 10^6 meters per second. By what percentage do the classical and relativistic momentum differ? Okay, so this is for the hydrogen atom. So the classical value for the momentum of that electron is mass of that electron times the speed, mu, MEU. The mass of the electron is 9.11 into 10 power minus 31 kg times the speed is given as 2.2 into 10 power 6 meters per second. So if we work that momentum out here, we are going to get, maybe let's retain this expression so that we can compare that with the relativistic value, which is gamma times MEU, where gamma is, for this velocity, if I calculate gamma, I'm going to get 1.0002689 if I take this as U in my expression for gamma. So that is this value. So if I substitute that here, I'm going to get the difference, right? So that is 1.000002689 times the mass of the electron is still 9.11 into 10 power minus 31 in our expression, multiplied by 2.2 into 10 power 6. So the momentum units is kg meters per second. Very clear right here. Now what is the percentage change? That is the question here, right? So the difference is, again, we have to calculate the difference or the fractional difference, just like the previous problem, the fractional difference or change The fractional change in momentum is given by the relativistic momentum minus the classical momentum over the relativistic momentum. If I calculate, I get the 2 point, this is fifth decimal, right? So 2.689 times 10 power minus 5 over this value whole thing. That is 1.0000268 times the 9.11 into 10 power minus 31 uh, into 2.2 into 10 power 6. Of course, in the denominator, once you do the difference, the remaining terms are going to be the same. So they are going to be there 2.2 into 10 power 6 into 9.11 into 10 power minus 31. All those terms are retained. So if I work this out, I'm going to get in percentage change in momentum by multiplying by 100, right? Percentage change I'm going to get. That percentage change is going to be this difference. Basically is the difference. This is not significant anyway, and these are terms common that are. So if I do that out, I get the 2.689 into 10 power minus 3 percentage. That is approximately 2.7 into 10 power minus 3 percentage. After multiplying by 100 here, this particular thing I multiply by 100, I get percentage change. That is a conclusion. Right. The seventh problem is an electron and proton are each accelerated starting from rest through a potential difference of 10 million volts. Compare the classical and relativistic momentum. So here acceleration of a charged particle is involved. Here in this case, both electron and proton are accelerated through 10 million volts. What are their energies in that case? If both electron and proton are accelerated through 10 million volts, 10 million volts, million is 10 power 6 volts. Then the energies, in this case, we're going to say acceleration potential is this. So directly we can write energies for both of electron as well as proton is 10 MeV, right, in EV units. The charge of the electron, we know E is equal to 1.6 into 10 power minus 19 coulomb. Of course, the charge for the proton is also the same. In this case, for electron it is negative, whereas for the proton it is positive. The magnitude of the charge is the same. Now we know the classical expression for electron. For electron, first let us write the classical expression for energy. For electron, classical momentum. For that classical energy, we can directly write, right? Classical uh, um, expression for kinetic energy, classical Ke, is we know that half mv squared. So Ke or K I call that here, like for simplicity, is half mv squared. This is a classical expression where E is the velocity of the electron, or half mvu square also we can use. Now this can be manipulated and written as in terms of momentum, because if we multiply by that m and divide by m, we get p squared over 2m. So K is equal to p squared over 2m. This is after making the m as m squared and p squared, dividing it by m. That is p squared over 2m. That is K. So from this I can write the momentum expression P is equal to square root of 2m capital K, where K is the kinetic energy. So this is my classical expression I have to use for momentum in this case, right? So because I have the mass of the electron, I know mass of the electron in terms of MeV units, mass is rest mass of the electron, right? Rest mass of the electron is 0.511 MeV over c squared units, right? So that I can use here in this case directly. Kinetic energy K is directly, I will use 10 MeV units, because all the units have to be in MeV, so that I can easily work out the momentum in MeV over c units. My momentum will come in MeV over c units if I do this. So I do this classical thing here. P is equal to square root of 2 times m is 0.511 times k is 10. So that is going to give me 3.20 MeV over c. This is the classical momentum for the electron if it is accelerated by a potential difference of 10 million volts. Now I can use relativistic expression to calculate relativistic momentum for the same electron. Relativistic P. If I do that, I have to use, of course, gamma m, V in this case, gamma m V. But then we will get stuck at gamma if we do the direct brute force calculation. So we have another interesting relativistic expression for P, and that we have to use here. So rather than using this, we will discard this because that will involve solving for u, which is going to get complicated. So rather than doing that, we have a simpler expression here, and that is P is equal to 1 over c square root of E squared minus mc squared whole square. We have derived this expression in our lecture videos, so please check out. There are two videos, one on relativistic momentum, another one on relativistic energy. So those videos contain derivation for all these expressions, so please do check out those videos. So if I substitute these numbers for P, I get P is equal to 1 over C square root of, here the expression is E squared, it is energy squared, that means total energy squared, right? Here in this case E squared is basically total energy squared, and that is the kinetic energy, which is 10 MeV, plus the rest mass energy 0.511. So we have to do that as a total energy. So that is going to be 10.5, roughly 10.5 whole square, E squared, minus mc squared whole squared. So mc squared in this case is rest mass energy, that is 0.511 whole square. So if I do that, I get 10.5 mgv over c as the relativistic momentum for electron. So using the same two expressions for classical and relativistic momentum, for the proton also I can do. So classical P for proton would be P is equal to square root of 2 mk. Here the mass of the proton is the rest mass for the proton is 938.3 MeV over c squared. This is the rest mass for the proton in MeV per c square units. So if I substitute that number here, and K I will retain as 10 MeV. So I get P is equal to square root of 2 times 938.3 multiplied by 10. So I will get 137 MeV per C. This is classical. So if I do the relativistic P for the proton using this expression, P is equal to 1 over C square root of E squared minus mc squared whole squared, I will get E squared here is added, total energy. So 1 over C square root of, it becomes 948.3, because 938 is the rest mass energy plus 10 MeV you are adding by accelerating it to that potential. So that is 948.3 minus this is rest mass energy, so it is directly 938.3. So within the square root, the difference in this case is just square of each of this, right? It's not directly subtraction, but it is square of these two things. And then there is C anyway outside. So if I work that out, I get 137.4 MeV over C. So here we can clearly see the difference between the classical and relativistic momenta is about 0.4 MeVs. So difference for this case, I write the difference in momentum between the classical and relativistic value in this particular case is about 0.4 MeV over C only, because it is 137.4, it is 137 MeV. But in the case of proton, we could see that it is more, because here it is 10.5 and 3.2. So there the difference is, we didn't calculate the difference then, but you can do that here. So the difference in momentum for the electron is more. It is 7.3 roughly, 7.3 MeV over C. But whereas for the proton, it is only about 0.4 MeV over C. Because of the higher mass here, by accelerating through the same potential difference, the difference in momentum is less in the case of proton compared to the electron. Okay, so let's move on to the next one. An electron has a momentum 90% larger than its classical momentum. What is its speed? In this case, it's very simple. The classical value is mu, p is equal to mu, whereas the relativistic value pr, let us call that as gamma mu. This is classical value. So just by comparing these two equations, that is gamma mu is about 90% larger than the classical value, that is about 1.9 times mu, because 90% you have to add to the classical value, so it is becoming 1.9 times mu. That means directly one can say that gamma is about 1.9. So gamma is 1.9. That means 1 over square root of 1 minus u squared over c squared is equal to 1.9. So if I simplify this equation, I'll get u every point, right? So I square on both sides, so I get 1 over 1 minus u squared over c squared is square of 1.9, and that is 3.61. So if I kind of rearrange this, my 1 minus u squared over c squared is going to be 1 over 3.61, and again I simplify it further, I get u is equal to 0.85 times the speed of light. So that is the speed of the electron which has a momentum which is 90% larger than its classical momentum. Right. Let's move on to the next one. Show that the momentum of a particle having charge E moving in a circle radius capital R in a magnetic field capital B is given by B is equal to 300 Br, 300 times Br, where B is the magnetic field, R is the radius of the circular path, where momentum is in the units MeV over C. B in Teslas and R is in meters. We have to show this kind of expression that we have to derive. Okay. So this case, we know that for a circular path, for the particle of charge E, its forces have to balance to be in circular path. That is, its centripetal force has to be balanced by the magnetic force on the particle, because it is in a magnetic field of B, Tesla's given there. So the particle of charge E is in a circular motion in a magnetic field. It has a charge, so its forces have to balance so that it remains in the circular path. The centripetal force mv squared over capital R, if R is the radius of this path, is balanced by the magnetic force, which is called the Lorentz force on a charged particle, And that Lorentz force is given by the expression for a charged particle. Generally, the force is called F suffix L as Q times the electric part plus the magnetic part, V cross P here. Charge Q. Here the charge is E, and we don't discuss anything about the electric part here. There is no electric field here. So the second term is QVB. So E times VB. Right. So these two forces have to balance. This is the centripetal part, this is the magnetic force part, and that comes from the Lorentz force, right? Second term of the Lorentz force. So these two balances, then we have a chance of, the particle staying in a circular path. So here I cancel this V and this V. There is one V remaining still, and therefore I get the momentum. In this case, mv is momentum, so it is momentum over r is equal to simply E times B. Okay, all right, so the momentum alone is E R P. So this is the expression we are getting for the momentum of the particle with charge E. Now if I do the momentum in MeV over C units, in this case, P in MeV over C units is equal to the charge of the particle is it's E, so it's electron, that is 1.6 into 10 power minus 19 times the radius is not known, so we can retain at R and B as such. R and B, magnetic field also numbers are not given, but we want to do it in MeV per C units, right? Because its momentum is otherwise in kg meters per second unit. So to convert that, we have to multiply by C, velocity of light, 3 into 10 power 8, and divide by the UV units, that is 1 MeV, because we want to get this in MeV, right? So here if I divide it by MeV, M is million, so 10 power 6, or mega, 10 power 6 into 1.6 into 10 power minus 19, because the conversion of 1 EV into joule is this value, right? So this conversion factor is again 1.6 into 10 power minus 19. That happens to be the charge of the electron. So these two terms will cancel each other, and then this 10 power 6 will cancel this 10 power 8 to 10 power 2 now. So 3 into 10 power 2 is 300. R and B are retained. The left side we have momentum in MeV per C units. So it is MeV over C. 300 MeV over 300 RB. MeV over C is the momentum. These are the units. So that is what is asked to be proved here. So we have done that. So that concludes our 9th problem. We move on to the next one. Frank and Mary each are carrying a heavy metal sphere of 5 kilograms. Frank is in a fixed frame S and Mary is moving in another frame with relative velocity U is equal to 0.5 c with respect to Frank. If both Frank and Mary each throw their respective spheres along their positive y and minus y prime directions respectively in their own frames of reference at 0.1 c, the spheres collide and rebound back to them elastically, show that their linear momentum is conserved for each of them. Now this is to do with the idea that relativistic momentum for observers in relativistic motion, in relative motion rather, there are going to be different values, right? That is idea here. Now the question here is, we have done, in fact, the derivation of relativistic momentum using this fundamental idea, measurement of momentum across different frames of reference. Here there are two different frames of reference. One is the frame fixed to Frank, the other one is the one fixed to Mary, and these two frames are moving with relative velocity 0.5 c, first point. Now if a sphere is thrown by Frank, let us say upwards, that is plus y direction, Now Mary is throwing her spear in the downwards direction, that is minus y prime direction. That is Mary's frame of reference. Now these two spheres will eventually collide and rebound back to each other. That is what is given in this question. We have to show that the linear momentum is conserved for each of them. Okay, so in this case, we have to use the expression, relativistic expression for linear momentum, that is P is equal to gamma times m. In this case, there are two velocities, remember. One is the velocity of the sphere that is thrown in each case, and the other one is the velocity, relative velocity between the two frames. Frank and Mary are moving with respect to each other. Maybe Mary is moving this way and Frank is moving this way, or Frank is at rest, Mary could be moving, but the relative velocity is 0.5 in this case. If that is to be taken into account, here it is gamma times, let us say m v naught. I take the velocity v naught as the velocity of the relative expression for linear momentum. Therefore, our gamma times, in this case, the gamma is equal to 1 over square root of 1 minus v naught squared over c squared. So there are two things here. U is the relative velocity, whereas v naught is the velocity of the particle which is moving. So we have to consider these two frames now separately. There is a Frank's frame. Let us call that S frame. Frank is moving, let us say in S frame, whereas Mary is moving in, let us say S prime frame. So momentum of the sphere in Frank's frame, let us first do that. Frank in S frame. Momentum. Let us call that a P of Frank in S frame anyway, but his momentum of the sphere, rather here this case is, it's thrown in the positive y direction, so I put a suffix y here. I have to use the relativistic expression, so gamma m times v naught, and that is m v naught over gamma is 1 over square root of 1 minus v naught square over c square. So the numbers are given here, right? The mass is 5 kilograms, and the speed with which this is thrown is 0.1 c. The sphere is thrown is 0.1 c. So I do that here. Let us say p of fy. So I multiply 5 times 0.1 c. C is 3 into 10 power 8. Over my gamma, I calculate for 0.5 c. For 0.5 c, if I calculate gamma, that turns out to be 1.005. So here I can multiply that. 1.005. Gamma times m v naught, right? So if I work this out, I get the momentum in this case is 1.508 into 10 power 8 kg meters per second. This is the momentum of the sphere as measured by Frank in his frame of reference. Now this is rebounding according to the question. So it is coming back with the same velocity in the negative direction. So if I do P, that is momentum for Frank in minus y direction, that is his frame of reference, that would be minus of the same value, 1.508 into 10 power 8 kg meters per second. Now since this is the thing, the difference in this case therefore is 2 times this value. So delta P of Frank, which is of course the delta P of Frank in y, his own direction, is minus 2 times gamma m V naught. And in this case, therefore, that is going to be minus 2 times. Already we have calculated this gamma m V naught. That is 1.508. But here, if you use directly gamma, 1.005 times 5 into zero point 0.1 into 3 into 10 power 8. If you have to directly the expression, then we end up getting minus 3.015 into 10 power 8 kg meters per second. This is the value we are going to get for the difference in momentum, or change in momentum rather, so to say, of the rebounded sphere for Frank in his frame of reference, right? Now we have to do the same thing for Mary's sphere as measured by Frank, because same frame of reference in S, Frank is measuring Mary's sphere, because Mary's sphere is coming towards him and rebounding back here, right? So if Frank measures for this sphere, what would be the momentum? That is a calculation that we have to do now. So momentum of Mary's sphere, sphere as measured by Frank in his frame of reference. And that would be, because that is a relativistic momentum for him, for him the velocity itself is going to be different. He's going to measure relativistic velocity. He's not going to measure 0.5 c, because 0.5 is the velocity of the sphere as measured by Frank in his frame of reference for his sphere. Similarly, from 0.5 c is the velocity of the sphere as measured, sorry, not 0.5, it's 0.1 c. The question it is given as 0.1 c. Relative velocity between the frames is 0.5 c, whereas the velocity of the sphere is only 0.1 c. So here we can say that 0.1 c is the velocity of the sphere as measured by Frank in his frame, and 0.1 c is again the velocity of sphere as measured by Mary of her sphere in her frame of reference. But 0.1 c is not the velocity of Mary's sphere as measured by Frank. That is a different value. So if I say that velocity of a Mary's sphere is Vm, that is going to be velocity of Mary's sphere in the x direction squared plus velocity of Mary's sphere in the y direction squared. Right, because it has two components. Right, so we know that this is V naught. This is V naught. So in this case, therefore, we can rewrite this velocity of Mary's sphere as my using our convention. Squared is equal to this V naught square is going to get affected by 1 minus V mx squared. Right? This is the expression. And therefore, for this Vmy, we will substitute that. Vmx is actually this V naught again. That's the relative velocity here, right? So this is the relative velocity because Mary is moving with respect to Frank in this direction. So whatever is the relative velocity of the two frames, relative motion in relative motion, that would be the x component in the x direction. Y direction, there is no motion between the two frames. On the x direction, there is a u is equal to 0.5 c motion. So that will be Vmx here in this case. Therefore, our Vm is equal to square root of 0.5 c whole square plus this whole thing, that is 0.1 c whole square 1 minus 0.5 c whole square. Again, another bracket, that will be 0.25 c square. That is 0.1 c square multiplies. So if we do this one thing, Vm, we get finally as square root of 0.325 c square, which if I take the square root out, 0.57 c. So So this is the speed of Mary's sphere as measured by Frank. So according to him, the velocity of Mary's sphere is Vm is equal to 0.57 c. Right? And again, we can further continue here to get the conservation, prove the conservation, right? So in this case, momentum of Mary's sphere as measured by Frank is therefore equal to minus uh, gamma times mv naught, and this extra term is going to come up, right? Because he's measuring in his frame. If you so directly work this out, it will be minus mv naught square root of 1 minus u squared over c squared, where u is the relative velocity between the two frames. And here in this case, another 1 minus, where we have here different gamma here. Gamma will not contain this u. Gamma is different from this square root term. That would be the relative motion, that is Vm squared over c squared, because the velocity is, because in the x direction, the velocity is this. So accordingly, gamma in this case is going to be different. So we have to calculate another gamma here, that is square root 1 over 1 minus Vm squared over c squared. That if I substitute, I get 1.217 for gamma here. Right? So if I put that number here in this expression for gamma, and remaining numbers are same, so I put that, I get P of Mary in y is minus 5 into 0.1 c square root of 1 minus 0.25 into gamma 1.217. If I multiply it separately, I get this number to be 1.581 into 10 power 8 kg meters per second. This is the momentum as measured by Frank of Mary's sphere. Now again we can do the same difference like we did earlier. So the difference in this case is uh, del P of Mary as measured by uh, Frank in y, right? That is del P my, which is obviously del P also for Mary. Why? Because in the y direction also there is a momentum change, and that is equal to 2 times m or v naught over square root of 1 minus v naught square over c square. This is basically the relativistic expression 2 gamma mv naught that we did earlier, right? This is the expression here we are using. So if I plug in the numbers, I'm going to get a 2 into 5 into, because 5 kg is the mass, 0.1 times 3 into 10 power 8 into the gamma here is 0.005. Right? If I do that, I'm going to get again 3.015 into 10 power 8 kg meters per second. So we can clearly see that in the original case, we got the same value number with a negative value here. Here we are getting that the positive value. So the change in momentum therefore is del P m x plus del P m y, and that is going to be 0, right? So therefore we have proved here that the momentum is conserved, right, for both Frank and Mary in their own frames of reference. Of course, I have shown only for Frank that it is conserved, but the same way, if you repeat the same thing for Mary also, you would be able to calculate the momentum of Frank's sphere in Mary's frame of reference, and you would be able to show that again there also momentum gets conserved, right? So that concludes some of the problems that we wanted to do on the topic of relativistic momentum. Thanks for watching.